Okay, watching the thunder and stuff, not looking good. So I thought I would reduce the pain and just come take care of this video. Hope we pull it out, but all right, I'm getting tired. Gotta go to bed. All right, so this is class number 3. The 1918 um, Spanish flu, they call it Spanish flu, but really started in Fort Riley, Kansas. I thought this is interesting as it's a topic of discussion, that you are supposed to wear a mask. It says here, wear a mask or go to jail. And so I looked that up, and people did actually go to jail. In fact, some even went to prison. They weren't wearing masks. The other funny thing is, even in 1918, people were still wearing the masks. Even then, people were still wearing the masks wrong, under the nose. All right. So a little tidbit there. Let's talk about some announcements coming up. Now, this is the new way I do the homepage. So there's much more information here. Where today we did first and third hour, and the link to the live Zoom, just click on that. Remember, the meeting ID is always, it's always going to be that. I may change the passcode. So if you're trying to get into the Zoom and it's not working, I'm going to keep doing Zoom this week. I might change to Google Meet if Zoom continues to have some issues. But anyway, so Zoom this week. If you're not getting in and the passcode's not working, then just change it. Go back, look at the homepage, and it'll say something different there. I'm going to keep it ASCII third. That's what it was last week, and we have not been Zoom bombed by anybody, so I think we're okay. But if we do, then I'll change that. Of course, virtual students can come to any of these Zooms they want to, or they can just instead watch this live Zoom. Well, this isn't live; it's live now, but you'll see a YouTube video of this starting tomorrow at noon. You should be able to. Let's see. Also on here, there's going to be, it'll have what you should have completed by that time we Zoom, or by the time we have class. And so it's a little bit confusing here. It's just all you're supposed to have. People thought they're supposed to have all of packet 1 done. No, it's just the exit quiz number 2. Okay. And then it tells you here whether you have homework or not. And today, or when you watch this, the only homework is exit quiz number 3. And I've added to this since, exit quiz number 3. And then try and join our ASCII Facebook group. So far we have 53 members, and there's about 85 of you. So that's getting there, doing a little better. I'd like to end up with 100. The reason I say 100, even though there's only 85 of you, because I do invite some teachers and a few teachers and alumni that would be there to help you. All right. Also, there's another one on there. I'll talk about that at the end of what else I want you to do. Okay, so we're not going to go over all this. It's all about the same. Of course, Thursday coming up, we have the Norman North game at Harv Collins this year. All right, so Spirit Week. I wanted to show you this at the bottom of the page. There is, at the home page, there is this question board. And no one's really used it yet. If no one ends up using it much, I'll probably switch that to something else, some other link. But the question board looks like this, and it might come in handy. And I just want you to for there just to use that just for class questions, not for physics questions, not for what's Andromeda like, none of that kind of physicsy stuff. Just more like procedure and Canvas kind of questions and things like that. This is just for kind of to keep you informed as to what's going on in class. All right. Discussions is where we'll do the talk about physics stuff, or on Facebook or something. Okay, so speaking of Facebook, this is our group, and I changed this. I changed the picture all the time, but I feel like he had a chance to go far in politics. I know he wasn't in politics yet, but I felt like he was going to get into politics, and he could have gone far. So um, I, I could even see him as president in 2032 was my prediction that he would be running at that point. So shocking that that happened. Very sad, very tragic. Anyway, so the point there was that you should join the Facebook group, and I'm putting units in there. There's all kinds of ways to get points. You don't have to join the Facebook group, but um, it's a pretty good way to communicate with everybody. Okay, including me. On the on the modules page, just to remind you again that the wrap up. This, if you're watching this wrap up, then you know what I'm talking about. I got that messed up. If you're watching the wrap up, then you know how to find that. But there's where you'll find all those, and then there's the packet one sheets. Okay. If you need to get to the copy. And then something weird, a student asked me, why is my grade like 4 point, where's this partial grading, or how did I get 4.38 out of 5? And I wondered that myself. And then I realized that when I made the test up, this is quiz number 2, that notice here, it says that I collected 8 points. So the whole thing is worth 8 points, right? Um, but then I couldn't figure out why it wouldn't give me 8 points. Went back and looked, and I guess a couple of days previous to that, I had set the point value to be 5 randomly, and then I guess Canvas doesn't really notice. That's weird. And so what Canvas did then was just weight graded it. So that's why it's a weird thing. I won't do that again. That was a mistake, but oh well. It's out of 5 now. The one you're going to take, quiz 3, I wrote that earlier today. It's going to be out of 10. All right, so I noticed about 1/3 of you did not take the second exit quiz, and they're not worth a whole lot of points yet. They'll be worth more, but it's important that you take these because it kind of gives me a feel for if you're getting it. Um, it it is sort of a check for you to see if you understand what's going on. Right now they're fairly simple, but they're going to get more complicated. So I pushed the due date. Sorry. I pushed the due date back to, I pushed it back to tomorrow night at midnight. So it was due last night, but I pushed it to, so give you a chance to take that. Or if you're watching this on Tuesday afternoon, that means you have till midnight Tuesday night. All right, I'm not going to push it back again. So it is a 0. A 0 would kind of hurt your grade at this point because there's not a lot of points. So do it. You get 2 shots at it, 2 shots at each one of those, I think. Okay. Still learning best way to do all this. All right. So back to the modules. This is something that we haven't taken advantage of this questions and discussion. That was from week 1, so we're not going to do that again. But down here, there's from week 2. So if you have a question about what we're talking about, that's a good place to go. Also, I went ahead and put those 2 quizzes in there. They were in the quiz section, and I guess you knew about them, but I went ahead and put them into the modules as well, so you can see, when they're coming up. Okay, I need to add the quiz 3. I see. I'll do that. And then, something I want to show you. There's this wrap up, this week 1 wrap up and preview of week 2. So I spent a little time on this trying to come up with like at the end of the week, I'll talk about what we did that week. And so these are the bullet points. Now to really understand it, you need to watch the wrap up video, or hopefully you were there at the live session, just look at your notes. But then if you go, okay. And then there's the preview for this week. So I wrote this last night, and now I see it's probably already out of date because on Monday we did not get to sheet 1.1. This is sort of like the weather forecast. It's just For about maybe 2 or 3 days, it'd probably be okay. But anything past 3 days is a joke as far as what, because that just depends on what happens, mostly in first hour, but what kind of discussion we have. And um, if we end up talking about stuff in other hours, then I got to go back to first hour and pick that up again. Because I want this class, it's not a static, you know, outline as these administrators want you to do. You can't teach physics that way. You have to. It has to be organic. It has to be taught through discussion and what comes up. So I have a best guess as to where we're going to be at the end of this week, but it's like I say, after today, it's already changed. So it's going to be rapidly changing all the time. But yes, we're still going to get 1.1. We thought we'd get to today, and we didn't because we got to talk about Andromeda and space time and all that. But that's okay. Um, so we'll start 1.1 tomorrow at the end of the week. All right. So just want to point that out. That's there for you. Okay. So that's it for announcements. Keep in mind, do join the Facebook group because you can ask me questions there. You can text me if it's an emergency. All right. So we were talking about this. We've been talking about this every day, and we realize that we can't sit still because even if we sit still in our room, we're still moving around the center of the axis of rotation of the Earth. Oh, I brought this up because I was trying to get the kids in the live sessions to take some notes, so that because it helps you to understand or remember things better and to start to focus, and it helps you organize your thoughts when you write them down on paper. So this is studies. It's not just me saying this. So that's why we keep a notebook and something about the whole pencil, paper, even if you're typing it in. If you're split screening it, you're typing into that still helps. It's better than just sitting there trying to listen. You have to take an active role. Okay, so anyway, back to this. So in Oklahoma, we're going at about 850 miles an hour, just sitting in the room. We're going around and around the center axis of rotation at 850 miles an hour. And then we broke this problem on Friday or on Thursday, Friday last week, and that is determining how fast we're going around the sun. And there's one sort of like that as far as unit analysis goes in the homework or in the exit quiz for today, quiz 3. Anyway, from last week we said, well, we'll take the distance equals rate times time from algebra 1, and we'll physics it all up. We'll make it so that it's applicable to real life. And that's what we did. We ended up with this equation right here, delta S equals V times T. And by the way, you're going to use this equation. You used it to find how fast the moon was going around the Earth. We used it to find how fast the Earth was going around the sun. And now you're going to use it in the quiz number 3 for just a linear situation where I'm riding my bike. Okay, sorry. Hey, we won. Oklahoma City pulled it off. It'll be a game 7, baby. See, it helped that I just kind of got away from it. Whew. Well, oh well. That's fantastic. Okay, so Wednesday night, baby, game 7 against the Rockets. It's going to be a barn burner. Wow, that's a good end to kind of a not so good day. All right, I cut up these all these peppers, and I was making this big meal tonight, and I cut these peppers up, and all that capsaicin got on my fingers, and it's oil. It's like an oil inside these peppers, and we grow our own peppers and all, and they get pretty hot, and it would not come off. I soak them in isopropyl alcohol, and then putting all kinds of detergent on there, dish soap, and man, their hands are still burning, but they've been burning for 3 hours, and finally I can't sleep. It's like 11 o'clock at night, and I can't sleep with burning hands. So hopefully they'll settle down a little bit. I'm going to go soak, after we didn't finish this, I'm going to go soak them some more. Anyway, sorry. So back to what we did. We did all this still kind of review. We did all this last week, and this was what we did in third hour. And we said, okay, so Gold standard is what we're doing. This was us trying to figure out how fast the Earth goes around the sun. And so all the stuff in yellow here, I got my little pointer here, all the stuff in yellow, this is the givens, So you start with your givens. And above is the symbols, and then down below is the numbers and their units. And then this little squiggly line right here, this means that I'm done with the givens. Now everything else is going to be a conversion. So the blue, my blue is the conversions. So I was trying to get it from some miles per year to miles per hour. And that's what this allowed me to do. So we got 66,000 miles an hour. That'll help you answer one of the questions on the quiz 3. Okay. And then, so now new stuff today. We talked about this and we said, well, okay, so we've got the Earth rotating on its axis. We have the Earth going around the sun. So what other kind of motions are there that we're going to deal with? And we came up with this, the idea that the sun itself is rotating around the center of the Milky Way. And that SMBH there, this SMBH, this stands for supermassive black hole. Supermassive black hole. So here's the sun with the planets going around it. It's going at about 500,000 miles an hour. That ends up being about 240 kilometers per second, which would put you from here to about Denton, Texas in 1 second. That's how fast we are. It's not just the sun, because the Earth's kind of tagging along with it. The sun's like the mother hen or the mother duck, and the Earth and Uranus and Jupiter and all, we're the little ducklings. So we're kind of going along in a corkscrew manner. And I put this in the Facebook group. It's an animation. It's like a 17-second animation. I may have it on here, but the Earth going in a corkscrew, because as we're going around the sun's moving this way. So we really go in a corkscrew around the center of our Milky Way. Okay. So we talked about this in class today, and the idea that a galactic year is the time it takes the sun to go all the way around the center of the Milky Way. And so we're really like a teenager right now. Here it is. Sorry, what's my problem? Oh, here it is. So the sun, I got a little thing here. So the sun, basically we're like a teenager. We're 18. So here's another picture of it, or a drawing, with the sun going around the galactic center. Now, we don't really go in a perfect circle like that, but that's the general idea. That's how we're rotating. So it takes us 250 million years to go around once. If you think about it, then the last time we were back in the same relative position in the sun to the supermassive black hole, the dinosaurs were, dominating the Earth. So this is kind of a cool little chart here. It talks about how long ago. So if you go back, the Milky Way started at 54 galactic years ago, way before our sun was here. Remember, we're 18 years old. The Milky Way galaxy is 54 years old. So oceans first came in early on. This multicellular organisms was about 7 years ago, galactic years. 1 year ago was that Permian-Triassic extinction. So dinosaurs are still walking the earth. And then humans came around. I'm talking about Homo sapiens, modern humans, came around about 1,000th of a galactic year. So now if you look at the future, in 22, the Milky Way Andromeda will collide. We'll talk about that in a minute. And then in 25 years, the sun will go red giant. So that'll be the end of our solar system. So basically, we will live to the age, our solar system lives to the age of 25. And we're already 18 years old. So we're actually 18.3 years old. So we've lived quite a long life. When I say we, I mean our solar system. All right, so the idea that we need to get out of this solar system eventually, I think Elon Musk is correct. And to do that, we got to get to Mars, and that's our first stepping stone. And it's not like something you can procrastinate and then eventually, you know. So humans will have evolved to the point that if we ever actually did get out of our solar system, humans would have evolved to the point that they'd be unrecognizable to us. I think we're still evolving, but mostly, mentally, I think. And then it's with AI, we're going to start to mesh with cyber. So we're going to end up with neural network that Elon Musk is also. I put an article on this on the Facebook group, but we're going to start to. They say the robots are going to take over. Basically, we're going to become the robots. Uh, It'll be kind of human robotic. So I think the humans will look and act much more different in even 200-300 years from now, much less a million. All right. Sorry, I'm not supposed to get off on that. So what brings Andromeda? Because when I was in college, I asked one of my professors, I said, well, if this is some physics thing, I said, well, if the universe is expanding, then why, and I read this somewhere, because back then we didn't have the internet, so it's like encyclopedia or something, or saw some nova, but the Milky Way and Andromeda are coming together. How can that be if the entire universe is expanding? And so we talked about it, but the idea was dark matter, some kind of dark matter this is the theory anyway, that is between Andromeda and the Milky Way, and that dark matter is attracting. Well, dark matter, and one of the world's leading experts on this is a woman named Lisa Randall. She's out of Harvard. She's also one of the experts on string theory. She's written some books, really pretty good books. But one of them talks about how dark matter could possibly be the reason why the dinosaurs went extinct. And that's a very interesting idea she has there. But the initial idea of dark matter came from a guy named Fritz Zwicky. I know you can't read this, or maybe you can. But Fritz Zwicky, 1933, a Swiss astronomer, came up with this because the physics doesn't work for the Milky Way. But once we didn't even understand there was different galaxies till the early 1900s. But by 1933, Fritz Zwicky is looking at the data, and he says that there's no way that there's not enough mass or matter in our galaxy, in the Milky Way galaxy, to hold all these planets in. They have enough tangential motion, they have enough momentum, they should be flying out, but yet they're held in somehow. And he said there's some kind of something that's holding it all together, and he called it dark matter. Well, that's too bad, because it gives people the misconception that this is some kind of material object, and it's not. It doesn't act like gravity. Neil deGrasse Tyson said that we should call it dark gravity, but I think that's a mistake as well, because it doesn't have the same properties as gravity. Gravity is something, things that have mass have gravity, but this is a different kind. So I propose that we call it dark attractors. And then there's this thing called dark energy, which is another bad term in my opinion, because when you think energy, you think, chemistry, joules, that kind of stuff. And we'll study energy here. But this isn't energy like that. This isn't, so energy is a bad name. So we have dark matter that we think is there's dark matter in the room right now. There's dark matter all around me. It's all around you as well. It's very diffuse. It's very diffuse. We just don't understand it very well, but it permeates everything. It's not like people think, well, dark matter is billions of years of light years away. No, it's right here in the room with you, and it's an attractive. It's not a force. It's like something with space time, but it's attractiveness of it that we still don't understand. You can go get your PhD and study it. And write a book and have your own podcast and all that, but become the world's expert if you want, because there's a lot of room for growth in this. its opponent is something called this dark energy, which I think should be called dark repeller, because what dark energy does is dark energy tries to pull. Dark energy, by the way, is also in the room with you, and it's trying to pull you apart. It wants to pull your left arm from your right arm. It wants to rip your arms out of the socket. It wants to take your fingers and pull them off. Then it wants to take your fingernails and pull those off. Then it wants to pull your eyeballs out. So this dark repeller is trying to pull everything apart, and that is part of this expansion of the universe. Like space-time itself is expanding, and the further away it gets, the faster it expands. That's the Hubble law that figured out by Hubble in 1925. So these are things we don't get, but it makes up most of the universe. We're only, what we can see is only 4% of the universe. That's the other like 96%. So we got a long way to go. We're just touching the surface of our understanding. All right, so enough of that. We'll talk about that more later. So the point is that we have all of these things going on. And I had some, I don't know if it's going to work. Yeah, I don't think it's going to work. I put this animation on, yeah, afraid of that. I put this animation on the Facebook group, but it's an animation of the Milky. Maybe we'll watch it Thursday, Friday, but it's an animation of the Milky Way coming into Andromeda. It's only like a minute and 16 seconds, but it's really well done. It was done a while back, and they've done other ones, but I still think this one's the best. So unfortunately, yeah, I thought I do have it queued up, but this is not working. So I don't want to have to share another screen, so I'm trying to keep this thing from getting too long. All right. So go to our Facebook group, and there's a unit called Physics Videos and Animations, and if you go there to the unit, you can click on it. You'll see it there. Or you just if you Google Andromeda, Milky Way, collision, animation, it'll pop up, and it's really cool because it's all computer models, of course, but it shows how they're going to collide. It's really awesome. So Andromeda is getting bigger and bigger in the night sky. When you look up there, in fact, already Andromeda is about the size. It's billions of stars, and it looks hazy with your naked eye. Now, if you get into a dark area like around Thunderbird or something, where there's no city lights, no light pollution, and you open up your camera, you have a camera, you can open up the aperture. You can maybe for a minute, you could probably get a pretty good view of Andromeda. But it's a spiral galaxy like the Milky Way. But thing is, every night it gets a little bigger. You can't hardly tell, but it's going to, like I say, it's going to take, the time it gets, sorry, I'm sleeping. By the time it gets 2.5, 3 billion years from now, it will dominate our night sky. It's all you'll see. It'll be like light, almost light at night, because it's a bigger galaxy than the Milky Way. So it'll eventually, if you look up, go to Google and search Milky Way Andromeda collision, and just do image search. It's really cool, all the different images, and I'll put one of those on as our Facebook cover here later on. All right, so I wanted to point that out. That's kind of cool. We'll talk about that more later too. So the point is that all of these motions, and Newton didn't know about all these motions, but in 1718 he proposed that there must be something. He called it the ether, and this correct spelling, the English spelling is aether. For Americans, we take out the A and just say ether. But he said there must be something that permeates all of space that is not moving. Like the Earth doesn't just hang in space with nothing. There's no there has to be some kind of matrix, and we can't see it, but it's there. It's called the ether. And so Isaac Newton was like, you know, a physics god. If he said it, you had to believe it, because by 1718 he was very well known. So this stood as this idea of the ether that was just it was just assumed that it was correct for about 150, 160 years, and finally these two guys here, Michaelson and Morely, at Case Western in Ohio, did at the time what was the most expensive experiment. It was sort of the Large Hadron Collider of its day. And what they were trying to do is an ingenious, something called an interferometer, but it was an ingenious experiment and if you want to look it up, it's really cool. Um, if we have time later, we'll talk about it. We're so rushed with this crazy schedule, so I can't get into all these details, but you should look it up. So um, the idea was that 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 there should be some kind of ether wind because the Earth rotates, and so there should be this. So when a beam comes this way, a light beam, and the beam comes this way, the one that's going with the rotation or against the ether wind should get there slower. It turns out that this is called an interferometer, but it turns out that but their conclusion was there was no ether. There's no ether, which is which freaked everyone out. That means that the space between the sun and the earth is a vacuum. I mean, they didn't understand how could a wave get from the sun to the earth, and it does, right? Light gets here 8.5 minutes, heat gets here in 8.5 minutes from the sun. And we think of, like, if I take all the air out between me and the speaker here, you won't you won't hear anything because you need a medium for the sound to travel and for the microphone to pick it up. So if there's no, so we knew that about waves, and we knew from Thomas Young's experiment in 1799, we knew that light was a wave. So it had to have ether, right? There had to be some kind of ether. And then this idea that there is no ether that's why they did this experiment for months trying to find it. Think, well, we made a mistake, or we need to make a better instrument, or we're just not picking it up. It's a little bit like what us finding gravity waves. It's the same. That's also an interferometer. It's a very big one. There's two of them. We have two of them, right? But that's the same idea. And we'll study that a little bit later. This idea of gravity waves. But so they kept thinking, well, our instruments aren't good enough, and it wasn't that. It just there is no ether. It's just vacuum between us and the sun. And so light doesn't require a medium to travel through, which was a big deal. That helped. This is about the same time that Maxwell's coming up with his equations. And so electromagnetics from about all the way back to 1820 with Faraday and Olmsted and all those, it really took off, especially with all this information. Okay, more about that later. So this is Michaelson and Morely. Also, it was America's chance to prove that we had arrived scientifically, because up to this point it was mostly, Europe, right? The Germans, the English, the French were the ones that dominated, and America was trying to, Ben Franklin. We had a few of good experimenters, but this was supposed to be the big breakthrough. But it turned out to be an experiment that was the null set. There was no. The answer was there is nothing. We can't find there's nothing. We just can't. It's just not there. So anyway, so you still hear people talk about the ether, and that's this mystical, like, oh, it got lost in the ether. So poets will talk about it, but it doesn't exist. Neither does the ether bunny. That's a physics joke. And Newton called it the luminous ether. So it comes down to this. We still need to be able to say that we are motionless, even though we know we can't be motionless. So your homework is to do quiz 3, to work on quiz 3, but also, and then join the Facebook group. But I also want you to practice being motionless by moving. Okay, it's a weird little riddle, but you've got to find a way to be motionless by moving. So we talked about it some in class, but this is your homework assignment. We'll talk about it more on Thursday, Friday. All right, so the things you have to do then, here's your to-do list, and I'm going to sign off. This thing's gone too long, so thank you for listening. I'll see you guys Thursday, Friday, and maybe Wednesday. Come by Wednesday and we'll talk or chat. All right, stop.